In this lesson, we will discuss Hilbert's axioms of betweenness. When we look back at the work of Euclid and Euclid's elements, we see that Euclid neglected to state some of the assumptions that he used in proofs. For example, he never assumed that points and lines exist. He never assumed the existence of non-collinear points, and he never assumed that every line has at least 2 points lying on it. So we made these assumptions explicit when we looked at the axioms of incidence, but Euclid also never made any assumptions about betweenness that are needed in some of his proofs. Although Euclid never mentioned the notion of betweenness, it seems that he used and assumed certain facts about betweenness that seemed obvious in diagrams, but he never actually stated betweenness axioms. In the 1800s, several mathematicians realized the flaw in Euclid's axioms. Mathematicians like Gauss pointed out that geometry required new axioms. In 1882, Moritz Pasch set out to create a much larger system of explicit axioms that were needed to prove all the statements in Euclid's elements. In 1899, David Hilbert incorporated Pasch's work in his presentation of his axioms. So we'll now present a modified version of David Hilbert's system of axioms. Even though David Hilbert's axioms were not the first system, his axioms are most intuitive and very close in spirit to Euclid's axioms. So far, we have considered the two undefined terms, point and line, and the undefined incidence relation of a point to a line. Hilbert's axioms are divided into 5 groups. We've already seen his incidence axioms. In this video, we're going to discuss his betweenness axioms, and then in the future, we're going to look at congruence axioms, continuity axioms, and axioms of parallelism. So let's remind ourselves of Hilbert's incidence axioms. For every point P and every point Q not equal to P, there's a unique line L passing through P and Q. For every line L, there exist at least 2 distinct points on L, and there exist 3 non-collinear points. In order to discuss the betweenness axioms, we'll need to first define this notation. So the notation with A star B star C, this is shorthand for the phrase the point B is between point A and point C. So by talking about betweenness and introducing the concept of betweenness, we're actually adding more structure to our geometry. For example, we're going to show that as a consequence of the betweenness axioms, every line must have infinitely many points lying on it. Thus, all the nice examples of finite geometries as examples of instance geometry will be eliminated as possible geometries under betweenness. So let's look at our first betweenness axiom. If B is between A and C, then A, B, and C are 3 distinct points lying on the same line, and point B is between C and A. So this axiom makes obvious the remark that between A and C is the same as saying between C and A. So it doesn't matter whether A or C is mentioned first. Now for betweenness axiom 2, given 2 distinct points B and D, there exists points A and C and E lying on line BD such that B is between A and D, C is between B and D, and D is between B and E. This axiom ensures that there are points between B and D and that the line BD does not end at either B or D. This axiom also shows that the points on a line do not form a discrete set like the natural numbers, where there's a number and then a next number and then no natural numbers in between. Betweenness axiom 3 states that if A, B, and C are distinct points lying on the same line, then one and only one of the points is between the other 2. This axiom assures that a line is not circular, because if the points were on a circle, then you have to say that each is between the other 2. Before we look at the next axiom, let's recall some definitions. the segment AB is a set of all points C such that C is between A and B, together with the endpoints A and B. So this is a definition we looked at earlier in the semester, but now I'm using the betweenness notation here. And recall that the ray AB is the set of points on segment AB, together with all points C, such that B is between points A and C. Next, let's look at a proposition that we can prove using the betweenness axioms. Proposition 3.1 states that for any 2 points A and B, the ray AB intersect with the ray BA is equal to segment AB. So in order to prove this statement, we're going to look at this as a set proof where we need to show that the left side is a subset of the right, and conversely that the right side is a subset of the left. This is a typical way of proving that two sets are equal. Well, by definition, segment AB is a subset of ray AB, and segment AB is also a subset of ray BA. So therefore, AB is a subset of the intersection of these two rays. So now we need to show that the intersection of the two rays is a subset of AB. So conversely, let's let C be any point in the intersection of rays AB and BA. We need to show that C is also in segment AB. Well, if C is equal to A or C is equal to B, then C is an endpoint of AB, and so then C is in segment AB. So let's assume that C does not equal A or B. So otherwise, we know that exactly one of the following is true by betweenness axiom 3. Point C is between A and B is between A and C, or A is between C and B. Let's look at the case when B is between A and C. Well, if B is between A and C, then C is not on ray BA, so that's a contradiction. If A is between C and B, then C is not on ray AB, which is another contradiction. So therefore, it must be that C is between A and B, and that proves that C is in segment AB. That concludes the proof of proposition 3.1. Before we look at betweenness axiom 4, we're going to need to look at this definition. Let L be any line and let A and B be points not lying on L. Then we say that A and B are on the same side of line L if A equals B or the segment AB does not intersect line L. And we say that A and B are on opposite sides of line L if A does not equal B and segment AB does intersect line L. So we see here on this example, A and B are on the same side of L, and points C and D are on opposite sides of L. Now we can look at betweenness axiom 4, which is also called the plane separation axiom. For every line L, and for any 3 points A, B, and C not lying on L, part 1, if A and B are on the same side of L, and B and C are on the same side of L, then A and C are on the same side of L. So here's a picture to go along with this. Now the second part of axiom 4 states that if A and B are on opposite sides of L, and B and C are on opposite sides of L, then A and C are on the same side of L. So here's a picture for axiom 4 part 2. Axiom 4 part 1 actually guarantees that our geometry is two-dimensional, since this does not hold in 3 space. Betweenness axiom 4 is also needed to make sense of Euclid's fifth postulate, which talks about two lines meeting on one side of a transversal. Next, a corollary of betweenness axiom 4. If A and B are on opposite sides of line L, and B and C are on the same side of L, then A and C are on opposite sides of L. Now we can define the side of a line. The side of line L is the set of all points that are on the same side of L as some point A not lying on L. Another way to describe this is a half plane bounded by L. So the side of L or a half plane bounded by L mean the same thing. Next, we're going to list several propositions. Proposition 3.2, every line bounds exactly two half planes, and these two half planes have no point in common. So the proof of this proposition is in the textbook. The next proposition is an application of the plane separation property to study betweenness relations among 4 points. Proposition 3.3 says if B is between A and C is between A and D, then C is between B and D, and B is between A and D. A corollary of this proposition is that if B is between A and C is between B and D, then B is between A and D, and C is between A and D. Proposition 3.4 is the line separation property. If A is between points C and B, and L is the line passing through all points A, B, and C, then for every point P lying on L, P lies either on the ray AB or on the opposite ray AC. And the proof of proposition 3.4 is also in the textbook. The next theorem, called Pasch's theorem, is a theorem that states a visually obvious property that Pasch discovered that Euclid was using without proof. It states that if A, B, and C are distinct non-collinear points, and L is any line intersecting segment AB and a point between A and B, then L also intersects either segment AC or BC, and if C does not lie on line L, then L does not intersect both AC and BC. Intuitively, this theorem states that if a line goes into a triangle through one side, it must come out through another side. The proof of Pasch's theorem is in the textbook as well. So here are some more results on betweenness and separation. Proposition 3.5, if B is between A and C, then segment AC is equal to segment AB union with segment BC. And further, B is the only point lying on both segment AB and BC. Proposition 3.6 states that if B is between A and C, then B is the only point common to the rays BA and BC, and ray AB is equal to ray AC. Next, let's talk about the interior of an angle. So given an angle CAB, define a point D to be in the interior of angle CAB if D is on the same side of line AC as B is, and if D is also on the same side of line AB as C. And so we can see that the interior of an angle is actually the intersection of two half planes. So if we look at this diagram below, the half plane below line AC and intersecting with the half plane above line AB would be defined as the interior of angle CAB. Next, proposition 3.7 states that given an angle CAB and a point D lying on line BC, then D is in the interior of angle CAB if and only if D is between B and C. So this figure goes with proposition 3.7. Proposition 3.8 states that if D is in the interior of angle CAB, then so is every other point on ray AD except for the point A, and no point on the opposite ray to AD is in the interior of angle CAB. So on this picture below, ray AF is not anterior to angle CAB. And part C, if A is between C and E, then B is in the interior of angle DAE. So we're going to use this fact in a proof in a few minutes. Next, we're going to look at the definition of betweenness with rays. A ray AD is between rays AC and ray AB if ray AB and AC are not opposite rays and D is interior to angle CAB. So here's an example of ray AD between rays AC and AB. We define the interior of a triangle to be the intersection of the interiors of its three angles. So looking at this diagram above, D is in the interior of triangle ACB. A point is exterior to a triangle if it is not in the interior and does not lie on any side of the triangle. Next, let's look at the crossbar theorem. So this result is labeled a theorem instead of a proposition to emphasize its importance. So the crossbar theorem states that if ray AD is between rays AC and AB, then ray AD intersects segment BC. So I'm going to give the proof of the crossbar theorem, but in order to look at the crossbar theorem proof, we need to consider the following figure. So I'll be referring back to this figure in the proof. Ray AD is between rays AC and AB, and we need to show that AD intersects segment BC. Point D is in the interior of angle CAB by the hypothesis, by the given information, and the definition of betweenness for rays. So next we're going to let E be a point such that A is between points E and C. And we can assume this by betweenness axiom 2. If we see again in this figure, the point A is between points E and C. Since line AD intersects segment EC in point A, which is between E and C, then E and C are on opposite sides of line AD. This is by the definition of opposite sides. Now, point B is in the interior of angle DAE by the way we defined our angles in step 1 and by proposition 3.8, part C. So then we can conclude that B and E are on the same side of line AD by the definition of interior of an angle. So therefore, B and C are on opposite sides of line AD by step 3 and the corollary to Betweenness Axiom 4. Since E and C are on opposite sides of line AD and B and E are on the same side. Now let G be the point between points B and C that lies on line AD by step 6 and definition of opposite sides. Then G is in the interior of angle CAB by step 7 and proposition 3.7. G either lies on ray AD or on its opposite ray by proposition 3.4. So let's suppose that G lies on the opposite ray. Then G is not in the interior of angle CAB by proposition 3.8 part B, and this contradicts step 8, which states that G is in the interior of angle CAB. So therefore we can conclude that G lies on ray AD. So this is the required point. We've shown that G is a point between B and C that lies on ray AD. So therefore AD intersects segment BC. So that finishes the proof of the crossbar theorem. The last proposition that we're going to look at with the betweenness axioms is proposition 3.9, which is two parts. It states that if a ray R emanating from an exterior point of triangle ABC intersects side AB in a point between A and B, then R also intersects side AC or side BC. And the second part, if a ray emanates from an interior point of triangle ABC, then it intersects one of the sides, and if it does not pass through a vertex, it intersects only one side.